Okay, ladies and gentlemen, let's rise to the next event. Ladies and gentlemen, we shall now listen to the recitation of the Holy Quran by Kevin Ulumul Fuadi, one of our students. Please.
السلام عليكم ورحمة الله وبركاته.
Waalaikumsalam
Waalaikumsalam
warahmatullahi wabarakatuh.
warahmatullahi wabarakatuh.
أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. يسألونك ماذا ينفقون قل ما أنفقتم من خير فللوالدين والأقربين واليتامى والمساكين وابن السبيل وما تفعلوا من خير فإن الله به عليم وما تفعلوا من خير فإن الله به عليم صدق الله العظيم. السلام عليكم ورحمة الله وبركاته.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Kevin Ulumul Quran. He is one of our students. Now, on behalf of the organizing committee, I would like to extend our warmest welcome to the Vice Dean for Academic Affairs, Professor Dr. Afika Sandi Safitri, MP. Thank you for your attention. The Head of Undergraduate Informatics Engineering Program, Mr. Supriyono, MCom. Our distinguished speaker, Mr. Atit Bashyal, PhD from Constructor University, Bremen, Germany. Welcome, sir. Respected lecturers of the Informatics Engineering Department and all participants of this international webinar, thank you for joining us today. Let's begin this event. Let us recite Basmalah together. Bismillahirrahmanirrahim. Ladies and gentlemen, we shall now proceed to the opening remarks delivered by the Vice Dean of the Faculty Science and Technology, UIN Maulana Malik Ibrahim Malang, Prof. Efika. The floor is yours.
Thank you, Buroro. Can you hear my voices?
So clearly, Prof.
Okay. Good afternoon, everyone. Good morning,
Good
Atit
afternoon.
Bashyal. Honorable guest speaker, respected lecturers, dear student, and honored participant. On behalf of the Faculty of Science and Technology, UIN Maulana Malik Ibrahim Malang, especially the Department of Informatics Engineering, it's my great pleasure to welcome all of you to this guest lecture session. And today we are honored to have Atit Bashyal, PhD from Constructor University, Germany, as our distinguished speaker. We sincerely appreciate his willingness to share his knowledge and experience with us. This topic today lecture is artificial intelligence in industrial energy management is highly relevant in today's rapidly evolving technological landscape, and artificial intelligence has become one of the most transformative technologies of our era, influencing not only the digital industry but also energy sustainability, operational efficiency, and smart industrial system. Through this lecture, we hope our student and academic community will gain broader insight into how artificial intelligence can contribute to solving real-world industrial challenges, and especially in the energy sector. So this event also reflects our commitment to strengthening international academic collaboration and exposing our students to global perspective and cutting-edge research. We believe that activities like this is essential in preparing our students to become future innovators, researchers, and professionals who are capable of competing in the international level while maintaining strong ethical and academic values. So to all participants, I encourage you to active engaging in the session, ask questions, and take advantage of this valuable opportunity to learn directly from international international event. So finally, I would to express my gratitude to the organizing committee, lecturers, and all parties who have contributed to making this event possible. So greeting from our Dean, Atit Bashyal, Dr. Agus Mulyana. He unable to attend this meeting because he has other activity in our faculty. So thank you so much for joining in the meeting in this morning.
Thank you.
Thank you very much. That's all for me. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, ma'am, for the inspiring and encouraging speech for the main session. Honorable guests and participants, we have now arrived at the main session of today's webinar. Without further ado, please allow me to introduce the moderator of today's session, Mrs. Linda Salma Angreani, PhD. How are you, Miss Salma? I hope you're
Great.
doing well. Okay. What time is it there now?
9:30
Oh, great.
p.m.
Okay. To our moderator, the session is all yours. Silakan, Bu Linda.
Okay. Thank you, Bu Roro. Assalamualaikum warahmatullahi wabarakatuh. Good morning, good
Waalaikumsalam
afternoon,
warahmatullahi wabarakatuh.
Bapak, Ibu, ladies and gentlemen. I'm Linda. I will be your moderator for this session. And during the presentation, please keep your microphone mute. And if you have any question, kindly write them in the chat box or use the raise hand feature. We will address the question during the Q&A session after the presentation. Now it's my great pleasure to introduce our distinguished speaker, Dr. Atit Bashyal from Constructor University Bremen, Germany. He is a lecturer and researcher whose work focuses on machine learning, knowledge graph, and intelligent industrial system. And now, Atit, the floor is yours.
Thank you, Linda. Thank you for a really good introduction. And my salam to everyone. And I'm happy to talk a little bit today about some of my research work and some of the things that I teach in the university and share some knowledge of what type of research and study works we are doing here at Constructor University. And also, if there are questions related to the topic, as Linda mentioned, we will discuss it towards the end. So without further ado, I will start my presentation for today. And I hope everyone is able to see my presentation screen. I think yes. So I will just start with it. So as already mentioned earlier, the topic for today's presentation is AI in industrial energy management, where I actually want to take you through a journey starting from data to how smart demand response happens is possible through artificial intelligence. The motivation for today's talk, or the motivation for this research topic, actually stems from the fact that traditional energy management system has changed because of how the whole landscape of industry has changed with information and technology, right? So traditional energy management used to ask us how much electricity did we use, or industries always needed to ask how much electricity did we use previously, so they can plan on the next upcoming processes to reduce or manage their energy needs. But with information technology and IoT systems in place, now a lot of industries can adequately measure their data. They are able to connect all of their systems through the internet, and there are also upcoming technologies that allow them to understand the context of data. They can put semantics into data, which opens up a huge knowledge base for the industries, and then they can decide how to act based on what data predicts or what data shows them. So AI enabled energy management has started asking not how much electricity did we use, but the question has changed to what can we safely change, and when can we change this, right? So in a sense, the change in the lens or the perspective through which energy management used to happen has changed, which means a factory or a cyber physical factory needs to be looked as a cyber physical systems where machines, data, rules, decisions, and external markets all interact together. So this has made energy management more of an information management problem nowadays, right? So moving forward to what I want to convey to you to our talk today, is first thing we will understand is why renewable energy has changed the way factories should consume energy, why this change in shift has happened. Second thing that we will look at is why good data engineering is needed before AI applications, right? So AI applications cannot do magic in a sense. So there is a need of good data engineering backbone for this to happen, and we will take a look at why this is required. Third thing that we will focus on is what are the problems that using AI models in industrial use cases can be. We will understand why these problems are there and how research works can be focused towards mitigating this problem. And finally, at the end of the talk, I hope everyone goes off of the talk with a message that intelligence in industrial energy management, or any kind of optimization task, or any production ready intelligence system, the intelligence is not only the AI model. So intelligence comes from the root of the task. So we will see all of these topics, and so our talk will circulate around this for today. So I will move forward with the talk. Um, the first thing, as I mentioned, we need to understand is why do industries need to change the way they look at energy management or they consume energy management, right? So as you can see, the old logic or the old way in which energy management used to work for industries is powers plants just adjusted the electricity level to match consumption, right? So what this means is, for example, let's say an electricity utility provider realizes that, oh, there's going to be some X amount of energy required for the next hour. What would the utility side do? They would ask the generating company to say, like, okay, you need to provide us with X amount of more electricity for X amount of time later on. So what would the generator do? They would maybe start the power plant. They would maybe add a generator increase the electricity generation. They would maybe turn on some nuclear plant or something, right? So this is how electricity market was continuously running. Depending on what the consumption is, supply would always go up and down. But uh, now, with renewable energy coming into the picture, everything changes, right? So with renewable energy, we cannot ask kind of the sun to shine a little bit more because we need more energy, or we cannot tell the wind to flow a little bit faster so we can generate more energy, right? So now we are dependent on certain natural events to generate electricity. So in this way, we cannot let the consumption side just consume electricity as they want. So we need to keep a system or some program in between that allows us to match the consumption with supply, or we match the supply and demand as we talk in economic terms, right? So demand response is a product or a program that has started in a lot of different countries. Germany has started adopting it since early 2019s, and our research work basically focused on how to enable demand response with artificial intelligence. And to give you a official definition of demand response, you could think of it as a strategy for shifting or adjusting electricity use in response to price, availability of renewable energy, or grid signals, right? So now, with demand response, what happens is, instead of the consumer telling the utility side that, oh, I will use this much more energy and you need to provide me with it, the utility side actually can respond to the consumer and say, like, hey, you can increase your electricity price, but it is going to cost you this much for the next hours. So they will send a price signal to the consumer, so the consumer can check the price signal and say, like, oh, maybe the price is more expensive for me, so let me see if I can shift my production to some other time where price is less. Or maybe the utility side will send a signal saying, we only have this much of energy available because we are constrained to use renewable energy. So maybe you can shift your energy needs according to what renewable energy prediction we have. All right, so this is the concept of demand response, and how the name also kind of reflects it, because the demand side actually responds to market signals in this case, instead of the demand side just increasing their consumption by their need. So to have a more clear picture of demand response, let's look at the graph, right? So in the graph, you can see the yellow line over here kind of traces the availability of renewable energy throughout the day. Mostly talking about renewable energy, as you know, the most popular one is solar. So this curve also kind of looks like a solar energy curve, right? So in the morning when there is no sun, like there's less energy. Throughout the day there's more energy produced, and then the amount of energy produced goes down. So the important thing we need to look at here is the red line. So what the red line shows us is what the factory's demand was before they looked at the signal, right? So they wanted to run their production in such a way that their production peak was somewhere around 7 a.m. in the morning and somewhere around 9 a.m. in the morning. But once they have the renewable energy signal, they know that the market or the electricity grid has electricity more during the time of 12 or like during midday. So maybe they can decide to change their electricity consumption peaks to match the peak of the supply, right? So this is in a uh, visualize this can actually kind of you can visualize like what demand response does. So if we focus on what changed over here, you can see that we did not actually save energy by magic. At the end, if you compute the amount of electricity total electricity used in the red line and the green line, the cumulative sum remains the same. So we did not actually save energy, but what we did is we just moved our energy need to a better time where energy might be cheaper in the electricity grid. Electricity might be abundant in the electricity grid, right? So um, instead of removing our energy need, we just decided to change it. Now, why does it matter? This matters a lot because the biggest problem with adapting renewable energy in the energy market is storage, right? So you cannot make enough batteries or enough storage systems to keep on storing renewable energy throughout the day and use it later on. The best way to utilize renewable energy is to consume it while it is being produced, right? So programs like demand response kind of help this change to take place, so that more renewable energy is consumed when it is available rather than waiting for storage or backup. And in a similar way, the industry in this way can lower their cost, because when supply is more in the market, obviously price is going to be less. So by using electricity during periods where price is less, factories are actually saving money also. um, Now, how does saving happen in a factory, right? One thing we need to understand is factory is not just a house with big meters. Residential energy needs are different than industrial energy needs, just because of the fact that in industry we cannot violate production, safety, comfort and quality constraints, right? So you can imagine in a house, when you decide to reduce your energy cost, let's say it's a hot 30 degrees Celsius outside, and you decide to not turn on your AC or fan, that's just taking away your comfort, and it happens in an individual level, right? But in a factory, your comfort can hinder other processes. Let's say like you decide to turn off AC or coolers for a little while, but the factory environment might get so heated that you need to close down production. So making even simple choices of turning off ACs or coolers in a factory for like small period of time can violate a lot of different production constraints, safety constraints and quality constraints at the end. So energy management in a factory level already brings a lot of problems over there. But one way of looking into a factory for energy management is to divide the factory into different categories of equipments, right? So usually what we do is we divide it into three distinct categories of flexible, semi-flexible, and non-flexible. So flexible uh, appliances means like they can move easily within a time window, so you don't need to think about constraints like, okay, if I shut down the machine right now and need to use it after 10 minutes, I can turn the machine on in 10 minutes and it will just start functioning, right? But for semi-flexible loads, let's say like ovens, production line, and storage chargings, um, it might be a little bit difficult to turn it off and turn it on a regular basis, because equipments like ovens require some initial prepping time to reach some temperatures, right? So if you have an oven that needs 10 minutes to reach its operating condition, once it's turned on, you cannot use that equipment or shift that equipment into a time frame when you need to turn off electricity for 5 minutes, right? Because you turn off the machine for 5 minutes, and later on when you need to use it after 5 minutes, you cannot use it there and then. You need to again wait for like 10 minutes for the machine to come to its operating condition. And there are some processes that will be completely non-flexible, like these processes cannot be changed at all. So with these different categories, we actually divide the factory into flexibility categories, so we can understand what machines can be turned off when, and what constraints do they have over there. So after this categorization, the key question for demand response then becomes, can we identify flexibility without violating production, safety, comfort, and quality constraints, right? So when we think about artificial intelligence for industrial energy management, what comes into question is, can this artificial intelligence system or this autonomous system identify flexibility without violating production, safety, comfort, or quality constraints? Um, but identifying this flexibility does not come so easily. And even though demand response seems to be such a good solution for the energy management in industries, it is not adopted by the industries at in a full scale, or industries are still reluctant to use artificial intelligence for such matters because of several different problems. And in the next slide, we look at these problems in short. So throughout my research as a PhD student, I focused a lot on identifying these barriers, and also identifying how to overcome these barriers to industrial demand response. And from my research, I have categorized them into five distinct categories. First of which is economic, which relates to the industry as a whole, looking at its economics, right? So the industry needs to look at what benefit does in industrial demand response bring to it, if they need to invest any new technologies in order for demand response to happen, and what are the basic tariffs that they need to pay for the utility side, or let's say the energy market, so that they can participate in such programs. So these questions already kind of point an industry towards, like, is it worth investing in demand response, or is it worth adapting demand response or not? When it comes to the technical barrier, which comes more into information system management. We start talking about how data is collected, what systems need to be there in place for these data to be collected, and what data quality can we expect to have in this sense, right? And then comes regulatory barriers, where it relates to market rules, contracts. Maybe sometime it relates to the industries being reluctant to giving out private data to third party in the electricity market. So these all factors also influence the choice of an industry to adapt demand response. The fourth category is social, which basically kind of relates to socioeconomics of us humans as in an organizational level, right? So this means like how much would we trust a third party to kind of control our electricity needs, or like suggest us on changing our electricity needs. So this comes more towards like the social science side of understanding demand response. And then comes finally operational barriers. So will demand response hinder the quality of product that I create in the market? Will demand response make me invest more in safety measures? Or like would I as an industrial manager need to change deadlines that I already have because of demand response? Or do I need to add more maintenance because of demand response? Like these all questions also play an important part for industries to adapt to demand response. So an important lesson that we could learn from these research topic was that AI solutions, if they need to be used for demand response, they cannot just be used as models, right? They now become a socio-technical system that must fit people, that must fit the thinking of people, that must fit the already existing infrastructure that a company has or an industry has. And it also should adhere to all of the rules that are already in place for the industrial systems. So in a big picture, although demand response is so beneficial for industries to adapt, and it shows direct effect not only for the industry but for so many other goals of renewable energy integration, reducing carbon footprint, because we are already reducing the use of big diesel generators, or fossil fuels in that matter, or like coal use for electricity production. So with all of these plus points, demand response still lags behind in adaptation because of all of these problems, right? And my personal research throughout my PhD, and also now during my postdoc research, focuses on the technological barriers of demand response. So when we come into technological barriers, we need to look at five distinct categories here, which starts from data acquisition and ends at security and privacy, right? When it comes to data acquisition, there is also a fact that research cannot solve the problem of data acquisition, right? Because high resolution sensors and meters are already available in the market. Now it's just the question of, is it already in place in the industry, or does the industry need to invest a little bit more to make data acquisition happen? So data acquisition kind of stems out from the economic barrier of investment also, because at this point the industry needs to decide a lot on how much investment they want to put into data acquisition. And the last point on security and privacy, this then goes into the barriers of regulatory and socioeconomic thought process of the company, because Security tools and security designs are already there in the market. It's just a question of what and how much does the industry want to adapt it, right? So for us researchers, the remaining three categories become really uh, important or really interesting to look at. First is interoperability, which kind of points towards the question of why are not models easily generalizable, right? Or like, why isn't data easily usable in different scenarios? um, Second point that we focus on research then is computational complexity, right? So what computing requirements might be needed for demand response to happen. And the third point comes towards optimization, which directly relates to what AI applications help where, right? So in the coming next slides of the talk, we will focus on these middle three topics and look into interoperability, computational complexity, and optimizations. So when we start talking about interoperability, I wanted to first talk about the data engineering backbone and how it is tackled right now in industry, right? So data engineering in its sense, or in a general sense, means or points towards the fact of how do we collect data from where, and how do we conveniently store it in a location that further data driven applications can consume it, right? So mostly what happens in industry right now is industrial factory floors or industrial machines are connected with smart meters, or like different IoT equipments that allow data to be measured, right? And then these systems can send these packets of data through the internet as message queues. Maybe you take it as API calls from somewhere, or maybe the IoT device just sends out data as streams of events. So data engineers capture these streams, and then they do their transformation, they do the data cleaning, and they put it into a time series database, right? So what are the problems in these data engineering backbones is, first of all, we always see a lack of standards in data collection, right? Which results in AI applications becoming problem specific. We will kind of look at what this means in detail later on, what lack of standards in data collection means. But let's focus on like AI becoming problem specific over here. So what this means is, whatever work that you do to develop a model or an artificial intelligence model, it becomes problem specific to that particular problem because of data standardization, right? Which means you can only use that model for that particular use case, and the next time if you want to use the model for some other similar use case, you have to train the model again. You have to make sure that data is clean and the model can understand the data. And you can see how generalization then becomes a problem. Second problem is real-time decisions require reliable pipelines, right? So if you develop a AI application model for some specific task, and as a data scientist you are just developing that model in a notebook and it's not there in production, then you really don't know like if real time decisions can actually be made or not. So there needs to be reliable pipeline in place before AI application can come into, right? And the biggest question that we need to think as data engineers in this case is how to put context in data. So with the next example, these 3 points will become a little bit clear, I hope. So when we talk about lack of standards in data collection, we come to this term of interoperability again, right? So what does interoperability mean in general is that two systems are trying to say the same thing, but they are saying it differently, right? So let's see in example over here. Source system A is a device that is sending some energy measurement with a timestamp, right? So maybe the event stream that it sends out, or the API call that the data engineer does, gets this following data packet. So like they have a device ID, they have a field called kilowatt hours, and they have a field called timestamp, right? And let's look at source system B, where it's sending a data packet with a sensor field, energy produced field, and time recorded field, right? As a human, or as an human who looks at this data and knows that okay, both of these data come from a device, right? So you would already make a idea that okay, maybe device ID and sensor mean the same thing, because device ID also points to a name, and sensor is also categorizing what sensor is there. So these two columns actually mean the same. Similarly with kilowatt hour, what it's trying to show is the amount of produced power or amount of consumed power, or it relates to power somehow, right? But and then energy produced over here also relates to power. But because the fields are named differently, unless it's a human who's reading this data, AI systems cannot safely compare them, right? Because for AI to understand device ID and sensor means the same, it needs more extra information or more grounded problem. So what happens is like when different names, formats, units, and meanings are different in different data, a unified model that is usable across every use case is difficult to build. So that's what the biggest problem that we mentioned over here, right? The lack of standardization in data results in AI applications becoming problem specific. So if you build a model for source system A, your model will be built in such a way that you cannot even start using it in a different source system, because your data is not standardized at all. Or if you have a big data engineering team and a big data science team, what you do is like either you make the data from source system B kind of adhere to the same standards and naming conventions used by source system A, so that your data gets unified. But if you want to automate the whole DR process, then it would never be possible unless interoperability in data can take place, right? So what our research team does, or what our research team looks at this problem is by adding a semantic layer in the data engineering backbone. So as you see over here, I have said I have also named the slide as the data engineering backbone reinforced, because as you see from the traditional data engineering pipelines, before the data can be used by AI application, what our research team is focusing on is developing semantic layers that can give context to data. All right, and then once data has context, this contextualized data can be used for a lot of different use cases, among which one could be generating knowledge bases, or extending models into general foundation models, right, which is applicable to all use case scenarios. Now when we talk about this semantic layer, we need to understand like what's the technology, or like how does this semantic layer come in place, or like how is it built. So in the next slide I will focus on that topic. So when we talk about semantic layer, what we think about is a shared vocabulary for data, right? So this layer should be able to build a shared vocabulary for different types of data. One of the concepts that we use in such semantic layers is the concept of ontology, which has been in market for a long time, but its use case has not been so immediately seen in the market, or like in research fields. But then interestingly, nowadays, since large language models have kind of come into the market, a lot of people have now understood that giving meaning to data, or having a shared vocabulary of data, is really important. So if you go today into the job market and search for like ontology engineer or knowledge based engineer, these job profiles are popping up now, because people are now realizing with LLM models that there needs to be context given to data, right? So ontology is not something new that our research group kind of came out with to standardized data. It's something that has been used for a really long time, but it had been let's say ignored for a while. And our research team started to look into uh, the use of ontology to create shared vocabulary for semantic layers. And in a sense, or I should say, fortunately, the market is also kind of moving towards now adapting this process of putting shared vocabulary into data. Just that was just a small divergent from our talk, but coming back to the talk, let's see what an ontology actually is, right? The ontology can be defined as a structured representation of concepts and relationships for a particular domain, right? In general terms, you could think of it as dictionary for data. To make this concept a little bit clear, I have also put this image of manufacturing ontology. It's called Mason. It's the industrial term used for the ontology. And as you can see over here, what the ontology actually does is it represents different concepts, right? So there might be an assembly line in the industry. The assembly line will have a product, or it will have an operation, right? So the assembly line will schedule a particular operation. So you can see not just that the concepts are represented over here, but there is also relationships between the concepts. So as you see, while we use ontology, we are not just giving information to data, right? So for example, we do not like, if some data has a product ID, we would then match that product ID column of the data with the product class in an ontology, right? Like, this is how we would kind of map things into data. But once we match a product column to a product ontology, it just does not end there. Maybe if we have another table that is, or another database that's related to operation, we can also connect data from that database, or like data from that table into the product table, because of this relationship that shows that product needs to be part of an operation. So as we map data sources into ontologies and create this data enriched with metadata, what happens is we end up building a knowledge base, right? So if you have heard in the market, or because nowadays a lot of AI companies are adapting this, and if you have heard the term of like knowledge base, or like LLMs doing knowledge retrieval from graph databases, this is what is happening in the background. So and ontology also, like as you can see, kind of functions as a graph also, right? So we are storing data in graphs that have meaning, and with these graphs we are automatically giving meaning to data. So our data now is kind of stored in a graph database, or people also like to call it knowledge databases, right? So this is what exactly a semantic layer is. So what it does is, you basically in this image, as you can see, there are various sources of data in the industry. These data are transmitted in different formats. What we do is we capture these data from different formats, we map these data into concepts of ontologies, and then we store it in a knowledge base or a graph database, so that we just don't have data, but we have data with meaning and context with us at the end, right? And now this opens up a lot of different application fields for AI application. And not only the problem that we looked at of generalizing AI models, but now it also opens up a lot of different scenarios for large language models to be used over there, because now large language models can interact with your data which has context, and you are giving grounded information to the large language model. So in today's context, because our research had happened before large language models came into the market, but I just wanted to add that in today's context, like having a semantic layer or a knowledge database does not aid on data interoperability, but now seeing the trend in market, it's also aiding the use cases of large language models, AI workflows, and several different things, which is now open to industry. And personally, for me, it's a really interesting topic, and my postdoc research is also focusing towards how large language models and AI as large language models can be now used in industrial use cases, along with knowledge base, right? So moving on from the semantic layer, for interested students who are here in the talk today, I also have put some suggested readings, which are published paper from my work together with my PhD supervisor in the university. And all of these topics are related to creating semantic middleware for demand response. In these papers we talk in detail about like how ontologies are mapped with data. We talk in detail about what kind of algorithmic concepts did we develop for these mapping components. There are paper that also talks about retrieval of data after we store it into a knowledge database, because for people, as knowledge databases and ontologies might not be is not so used in practice, then interacting with the data becomes difficult, right? So instead of using complicated querying language, we also developed products to where people could just type in natural language, saying like, what was the production of electricity yesterday at 12 p.m., and then you would retrieve the answer. So I should mention that if you go through the paper, we did all of these research before large language models were there. So we use a lot of NLP techniques, and traditional machine learning methods to match tokens, match classes, and develop this big machine learning model for natural language to query uh, uh, workflow. But now with large language models, like our whole big model can be replaced easily, right? So that's why my new interest in research is towards understanding the limits of using large language models in industrial energy management with semantic layers, right? But for interested students who still want to understand more about the semantic layer, more about how ontologies can be used to enhance data interoperability, and also how linked data or like enhanced, semantically enhanced data can be used for sustainable manufacturing, you are you can go through these papers and understand more about the topic. Um, from the next slide, I move towards another topic, moving from interoperability towards computing complexity, right? So the three topics that my research focused on was interoperability, computing complexity, and optimization. So we come to the second topic of computing complexity. To understand computing complexity, we need to understand a newly coined term around 2024. The paper by Aldume et al. Was the first paper to coin this term called computing continuum. um, so what the computing continuum basically means is that it's a continuous flow of computing machines, right? So moving from low level devices such as endpoints that just generate data and might not have enough computing requirements to do processes, to to moving through like hierarchy of computing processes, going from endpoints to edge layer, from edge layer to fog layer, and fog layer to cloud. So like this serial movement of data kind of happens in a continuum, right? So computing is also now not isolated in different places, but computing also becomes continuous right now, because before waiting for the data to reach the cloud and running some models or some optimizations in the cloud, now what we can focus towards is like how to make these things happen before the cloud. It could be because of like reasons like security reasons, that some industry does not want to send their data all the way to the cloud, so like things need to happen in like certain edge layers that are in the industry, right? Or maybe the data before it reaches the cloud needs to be transformed in a certain way to reach the cloud. So like we focus on running transformation applications on these continuums, so like in the edge or in the fog layer before it reaches the cloud, right? So when talking about computing continuum in our research, we actually used the continuum to enable semantic mapping to happen, right? So what we did was we defined a new architecture which decided like what are the data processing needs required at endpoint, up till like what communication infrastructure and core protocol are needed for this. And then we divided the continuum into three distinct layers: so endpoint, intermediate, and cloud. The intermediate layer over here means all other machineries or all other nodes where we can run computing before it reaches the cloud. So in market you will hear terms about that say like edge, fog. Now like there are also systems that lie between fog and edge, which I think are called mist layers. There are like layers that come after the fog layer. So like there is a lot of different categories that the industry, or let's say like the marketplace is making for these computing requirements. But for research to be made easy, we decided to put it into three distinct categories of endpoint, immediate, and cloud, where intermediate layer represents all the different possibilities that can be there in the market. I just wanted to mention, like, I have forgot to place the reading material here. Like, I just realized it, but I will update the slide with the reading material and send it to Linda, so it's with all of the students later on. These images that you see over here is also results of our research, and we have published it in our journal article that I will put the link to over here before I send the PDF. So in this journal article, we extensively work towards defining, like, if a certain layer needs to fit the intermediate category, what are the backend requirements that it needs, right? Like, what is the data processing requirement it needs. So like, this paper discusses this extensively, not only from a computing perspective but also from the communication perspective. So the yellow nodes define like what communication needs are required to be qualified as an intermediate layer, and finally, to be qualified as a cloud layer, what are the requirements, right? So we first define these requirements, and based on these requirements, we also kind of describe the best way to enable semantic mapping in an intermediate layer, right? So we run the semantic middleware application using containerized containers in Kubernetes, and then the semantic mapper and semantic storage works inside these Kubernetes pods in an edge machine, so that data is already semantically enriched before it reaches the cloud and is stored in the cloud, right? So for interested students in this topic, when you get the handout, I will have the link to the paper also pasted over here. um, and this paper also gives an overview of cloud technologies that are available in the market, given by either Google, Amazon, or Azure, which fit different categories over here. So it also is kind of like a manual for data engineers to understand what technologies to use where. And you can take a look at this, look at our paper to understand more about what the computing continuum is, and like how the whole paradigm of computation before the cloud is changing industry as a whole. Okay. Also, I just realized here, like, the paper also talks a little bit about security over here. So this is what you see, this boundary over here. I would not like to describe how this security is implemented by words, because I am not sure if I can do it. But if you read the paper, you will also figure out like how we tackle security by using messaging brokers in an immediate communication link node. And I did not place so much details of this because for bachelor students, like, understanding these computing concepts could become difficult. So if you are interested, please go through the paper that I will paste the link to later on. Finally, we come to I think a more AI related topic, which is like AI application areas in industry, right? And more focusing on industrial demand response. In this context, we look at two distinct categories. So first is artificial neural networks, and mostly the use of artificial neural networks in demand response is for distinct distinct profile generations. So like, for example, if you want to understand your load generation profile, or you need to forecast how much load a particular process might need in the future, like those kind of forecastings are enabled by artificial neural network. There is also forecasting of renewable energy generation, so like based on previous historical data of what has been happening in a particular power plant, we might um, forecast what the generation might look like for the coming days, coming weeks, right? Also for the coming hours. And final application area is also price forecasting. So for the utility companies to kind of forecast what is the best price for the market, depending on supply and demand. The second category of artificial intelligence use in demand response, especially in our research group, is reinforcement learning. And we usually use it for scheduling and control of loads, right? So it's mostly used for optimizing processes, scheduling loads throughout the day. Next, I will try to look into two distinct applications of artificial neural network and reinforcement learning, and we'll also try to show what are the problems with these methods that we are facing during, or we face during research, and like how we try to tackle it. First, AI application we look at is forecasting in general, right? So it could mean like you have historical meter data from which you want to forecast like the load, next hour load. You could also have weather forecast from which you want to forecast the availability of solar or wind, or as I mentioned, electricity price signals from the previous days, months, using which you want to predict the expected price, right? And the workflow for people who are used to machine learning uh, is the same as always. Like, we train an AI model using all of these data, and then we test and see like how good this model is generalizing, right? But in real world, in the industry, it does not always happen in this way. Why, do you ask? It's because of the fact that data is scarce, right? You never get complete data to always train the best model. um, so the question of why is data scarce in industry is because, first of all, maybe the industry might not be adequately equipped with sensors, so like incomplete sensors, so like you don't have complete data at all. Second point, even if you have sensors, there could be noise attributed to your data, right? So like your data is not fitting like a general profile. So like, while building the models, you will either try to reduce the noise, or you would ignore the noisy data points. Third fact could be short history, maybe like the data acquisition started recently, like maybe they installed the sensors last month and you just have 1 month of data, but 1 month of data is not enough to train an artificial intelligence models, right? You need like years and years of data to at least see some significant optimization from the model, or to see some significant positive results from the model. And finally, as we talked before, maybe there are data from different machines, but these data are not standardized at all. So maybe before even you start training a model, your first task would then to be collect all of these datas that are labeled differently, that you need to sit down, you need to look at these labels, you need to understand how these datas connect with each other, and maybe then you can be able to generate a big data set for your training. Now, does it mean that because data is scarce, like we don't try to build models at all where there is no data, right? No, we do try to build models there too. And what helps is techniques of transfer learning, or like recently after transformer architectures have become famous because of large language models, there is also this concept of foundation models that came about, where you build a big foundation model with all the data that you have, and then later on fine tuning for like other work, right? So no matter if you choose to do foundation models or transfer learning, you will need to do fine tuning in your target. So like in both of these concepts, what happens is, like, let's say you have a source where data is adequate, or like you have enough data to train a model. So you would train the model with data in the source, and then you would try to use that model in a target domain, or like in a different place, right? So before you can use the model efficiently, you need to do a certain optimization of the model in the target, which is also known as knowledge transfer, right? Knowledge transfer is important because what we need to look out for is, when we train a model in the source domain, what it learns actually is it learns patterns that is present in the data at the source, right? So when you take this model and use it in the target, maybe you won't see optimal results at that point, because all the model has done is it has learned pattern from the source domain. So you need to optimize the target somehow. You need to optimize the model in the target domain too. But it becomes kind of counterintuitive, because didn't we want to do transfer learning in the first place because we didn't have data in the target domain, right? So like, how are we going to optimize the model again in the target domain if we don't have data in the target at all? So this was a question that came up during our research, during my PhD research, and is one of the topics that I focused on to understand what can be done in this case, right? So um, we came across this concept called domain adaptation, which is actually a method to train model to match complex representations of data. And what we figured out is that with domain adaptation in the picture, we actually need less data in the target domain to have good prediction results. So I will try to explain to my best, like the architecture that me and my research team developed, because it's a novel architecture that we developed and we have published it in a journal. So I think there is the link also for the reading of this article in detail about how we tackle the problem of limited data for domain adaptation. But in general, I will try to kind of show you the concept of what we did over here. So as you see in the image, it's distinctly labeled as 1 and 2 with different colors: green for the source domain and red for the target domain, right? When we talk about the source domain over here, this was a power plant. It was actually for a solar power plant that we did it during research. This power plant had data worth like 4 or 5 years of data, and which was enough to train a stable model. But the target domain, or there was some other solar plant for which we also wanted to have a forecasting model, but the problem over there was the solar plant was recently installed, and they just had, I think, 8 months of data with them. So we could not train and stable model for that solar power plant. So that's why we wanted to look into transfer learning. Then we tried different ways of transfer learning, and we always came up to the same problem, that the model learned so much good from the source domain that it was not generalizing good enough in the target domain. So our question then shifted towards understanding how can we create a forecasting model in the source domain which we can use without training in the target domain, but still we get good results, which is what motivated us to come up with this complex architecture that you see in the image. So what we actually did is we divided our model into three distinct components, right? So you can see dark green over here, encoder, decoder, and forecaster, right? Now what do these things do? So once you send label data to the model, the encoder just changes your data into a complex probabilistic representation. That's all it does, right? And the decoder then samples data point from this probabilistic representation and tries to reconstruct the exact input that was sent to the encoder. So in this way, the encoder decoder architecture is just taking your data, putting it into a probability space, and from the probability space the decoder is trying to reconstruct your same data. And parallelly, there is a forecaster also being trained that also samples from this the same probabilistic space and forecasts the labels for you. So like it's doing the forecasting for you. What we did in this model is maybe for people who do not have much knowledge on neural networks would not understand this term. Like there is a term called gradient taping. So what this means is like you are trying to optimize parameters for all three models at once, right? So the loss function that you are training has three parameters being tuned at once. And why did we try to do it at once? Because some people also might ask, couldn't you just train the encoder and decoder before and then train the forecaster after that, right? We also tried to do that, but with that what problem we were facing was the feature space was just being useful for the decoder but not for the forecaster. But when we trained it parallelly together, what happened was whatever, because this latent feature space or the probability space that we are talking about over here, it's a black box, right? So we as humans do not have a way of understanding this, or we do not have a way of even seeing like what this looks like. It's just in a big complex model, it's a black box, something is happening and we are just getting the result. So what we saw that was that this parallel training, what it did was like it constricted the black box representation of data to also be represented in such a way that the forecaster was able to forecast your labels. So it was not only used for reconstruction but also for forecasting later on. So this was the training in the source domain. And then when we took the model and put it into the target domain, which you see down here in part 2, what we did was in this time we just trained two distinct models. So over here you can see it's just the red ones that we trained over here, so the encoder and decoder. What's happening in this case is like we took like the limited data that we had, and then we just put that data into the encoder and we trained the decoder to reconstruct the input data. And while doing so, we were also creating this latent feature space, or this probabilistic representation of data in between, similarly as in the source domain. But what we did in this case is, while we were training the decoder architecture over here, our loss function also included a term called the KL divergence. So mathematically, what KL divergence does is it measures how different two probability distributions are. So using this KL divergence, we were at each step of optimization measuring how my probability space in the target domain looks compared to the probability space in the source domain, right? So like it's measured by this parameter, and we wanted to minimize that, which means if the KL divergence is the least, that means my probability space of representing data is the same, right? And if there is a big KL divergence, that means the two probability distribution are different than each other. So like for a for example, like if you compute the KL divergence between two normal distribution or Gaussian distribution, depending on how wide the distribution is, the KL divergence might change. But if you compare two Gaussian distributions with the same mean and standard deviation, then your KL divergence is zero, right? And if you compare a Gaussian distribution with a binomial distribution, your KL divergence would like explode and go to infinity maybe. So like this way we can keep track of like how close probability spaces are with each other. And in this way, what we ended up doing was, by just sending in unlabeled data and reconstructing the data using the decoder, we ended up with a probability space in which data was represented exactly same as the way in the source domain. So the best thing about this training was that later on, when we took the forecaster from the source domain and used it without fine tuning, without any further training in the target domain, it worked perfectly. It was able to outmatch a lot of different algorithms that we compared as baseline, and which was a really good result for us. And we ended up publishing it in a journal article, which I have mentioned here for further reading, to understand the model more in detail if you are interested, because in the talk, like there is not much time to go through all of the mathematical details of the model. And also for all of the viewers who might not understand all of these mathematical concepts, you can take your time, read the paper, maybe also put the paper into your favorite large language models and ask it to help you understand the concepts there, right? So you can go through this related reading to understand how our model or our novel architecture was able to solve this problem of domain adaptation. Okay, so moving on to the second application, which was reinforcement learning. As I mentioned earlier, reinforcement learning is usually used for optimization of schedules and tasks in the industry, right? But for a lot of people, reinforcement learning by itself might be a new topic. So to give you a small overview of reinforcement learning, I have put this small pipeline over here. So what happens in reinforcement learning is, you have an agent that basically is kept into a simulation environment, right? So what this agent does in the simulation environment is, then it has to make action, right? So like, let's say your simulation environment is a factory where you are trying to reduce energy cost. Your agent might need to make an decision of turning off a certain equipment, turning on a certain equipment, right? All of these things based on uh, um some conditions in the factory. Now, how does the agent learn to make good actions is that it's always given a reward. So like once the agent is in the factory simulation, it makes a action. Then if the action was correct, or if the action was good for the agent, it gets a reward which is positive, right? If the action was not the best action to be taken at that particular time, it kind of gets a negative reward. So it knows like, oh, these actions are not good to be done, right? So if you think about it, like this is also intuitively the way we humans learn too, right? Like we do something, and then like later on we evaluate, like was our action good for us at that moment. And if we feel like no, like our action was not the good, then in the back of our mind, like we develop a reward system in which we are like, oh, like I should do this or I should not do that, right? So we learn by doing as humans. So the same concept applies here in reinforcement learning, where we are letting an agent learn by doing, and we are reinforcing its learning by giving it a reward when it does good, and giving it negative rewards when it does bad. But in industry, the hard part is not generating the reinforcement learning algorithm alone. The more difficult part is defining safe actions, realistic simulations, and useful reward functions, right? So definition of safe actions kind of also depends on like what kind of environment you are working with, and different things. So it also relates to realistic simulations. So like as long as you have realistic simulations, then your actions are also kind of safe, right? And reward functions are really difficult to develop. It needs a lot of input from industrial partners that know how things run in the industry, and that know like how things need to change in industry. So there's a lot of collaboration needed over there too. And one of the research that we kind of did during my PhD research, with reinforcement learning, was to develop a realistic simulation scenario. We were looking into a factory environment for steel production. And what was happening was, when we were using a single agent to make decisions for all of the machines in the factory, this agent was not able to do its work best, because it could not understand like how to make decisions for 10 separate machines which have different running constraints, different energy consumptions, and other parameters. So we had to kind of change the idea to make one machine as one agent. So like each machine can make its own choice as an agent in the factory environment, right? So this was the way we kind of defined the reinforcement learning problem. But then this definition became a bigger problem for us. So what happened was, like, we had a process
Atit,
simulation.
sorry for
Yes.
interrupt. You
Yes.
have 5 minutes for presentation. Is it okay?
Yeah, I will be
Okay.
done in time.
Thank
Yeah.
you.
So okay, so the process simulation was there. We developed a multi-agent environment where like we had several actors are like agents over here. We had different agents for each machine making a decision, and then where we had a critic that evaluated, okay, if these decisions are useful for the environment or not, right? So the scalability challenge that we faced over here was that when we added more and more agents, that meant each agent had to communicate with each other. The critic needed to understand what each agent had done. So the number of data point and the number of computing resources we required to run the model exponentially grew. And we were facing a really big problem on this matter. So what we did was we did a design response in designing the critic system over here. So we decided to filter information over here. And fortunately, at that time, transformer networks, which are the backbone of large language models, also had already come out in the market, and we tried to use multi-headed attention, which is also used by transformers, to solve our problem of filtering information. So now what the critic was able to do was it was able to look at all of the information from all of the actors or all of the machines, all of the information from the factory environment, but it was able to only filter useful information to it by using the multi-headed attention approach. And it was kind of like a test for us too, because even till today, when we talk about large language models and transformers, no one knows like how these models give attention to what, right? So it's again a black box. We tried to see if this black box technique would work, and fortunately for us, the black box technique worked, and we were able to publish this results also as a paper, which is listed here, where we were successfully able to optimize the use of different equipments in the factory floor based on the price signal. So as you can see, the image over here is also part of the publication results. These are like all different equipments in the factory. And as you can see, where the price was the highest for that day, like in this time, like nothing has been scheduled to run, and all other processes have been scheduled optimally to run the factory throughout the day. If you go through the paper, there is more detail on like what each machines are, like how each machines are there in the production line. So you will be able to see more clearly like how well the agent has done, because it has learned not only to shift prices, but it has also learned like how each machines are linked to each other. So like it's an interesting way to see what a black box model has been able to do in this case of optimization. um, okay, so we come towards putting the pieces all together. So I think throughout the talk today, I was able to convey my idea that the intelligence in industrial or intelligent industrial energy management is not only the AI model, but it is the way in which we connect data, in the way which we give meaning to data. It also, the intelligence also comes in which architecture we decide to choose, and also like finally the decision logic or the AI model is also important, right? So in any use case like this of industrial energy management, or even if you go into any other domain, intelligence does not only come from the AI model or just by using the best AI model, but I hope I was able to convince you in seeing that intelligence is a whole ecosystem of information management, which begins from connecting to the data, providing meaning to the data, choosing the best computational architectures, and finally on top, AI model or the decision logic is just the cherry in the top that everyone sees, but there are a lot of different layers that come before there. Right. And before I end the talk today, because I think the talk was more for bachelor's student, I wanted to point out some fields where students can find direction if they are interested in more data related topic. So like you could focus on data engineering topics, which is like you could focus on understanding what are the pipelines of moving data from one place to the others, what are cloud services used for data engineering, right? Or interested students can also move their focus into systems management, where they need to study more about processes and constraints, like reliability of IT systems, safety and security of IT systems, right? Another direction that you can find is in software engineering, where you will more focus on deploying a particular architecture, deploying in a particular architecture, deploying your model, deploying your data engineering pipeline. So or developing like human interfaces, like a user interface, or those things like that would come under software engineering for interested students. You can also look into directions of machine learning, where then your learning would focus towards like understanding forecasting models, like understanding how anomaly detection is done, understanding how what optimization techniques are there, and how optimization techniques work. Or another direction for students could also be, now I think is more relevant also, is semantic technologies and knowledge representations, because as I mentioned earlier, with the rise of large language models and with the rise in need to give grounded information to large language models, knowledge representation of data using ontologies and knowledge graphs are growing a lot. So this is also a direction where students can find themselves focusing on in the near future, if you are interested uh, in these topics. And yeah, as I mentioned before, data driven solutions like demand response, it does not need to be demand response, needs to combine needs to combine intelligence from several different domains, which include all five of these. So as for aspiring students who want to find a direction for their future, from my side, I would like to categorize these four different directions. And I would finally like to end the talk and open up for the question answer session. Thank you.
Okay, thank you very much, Atit, for the insightful presentation. Now we will move to the Q&A session. And everyone, if you have questions, please write them in the chat box or use raise hand feature. Okay, we will see. At the moment, we have not question yet. Maybe from the audience, you can raise your hand. Okay, I will check.
Saya dulu.
Wait.
Ini ada Bu Linda.
Ya.
Ya, ini sebenarnya ada pertanyaan titipan. Boleh saya bacakan saja pertanyaannya?
Ya, silakan. Oke, ya. Sure.
Ya,
From pertanyaan question from
Mr. Yakin.
Okay. Yeah, please.
When I was studying for my master degree, I researched unit commitment and economic dispatch. What is the current state of the latest research on unit commitment and economic dispatch? What new variables are included? What methods are used? And what constraints are applied?
Oh, okay. Thank you for the question. I kind of understand the question of like unit commitment. So like unit commitment is a way in which demand response can happen, right? So like you commit different units of electricity for different periods of time. But from my personal experience in research, I am not so used to unit commitment, because my research project that I had worked in collaboration with the industry focused only on renewable energy based price signals. So the goal was the demand response product that we developed and worked on was only based on like renewable energy signals. So I will not be able to kind of answer what is the current state of unit commitment in Germany and or further research questions on there.
Okay, thank you. Is there any question or is it clear, Mr. Yakin, for the answer?
And also
Okay.
yeah, also because I come more from a data engineering and
Yes.
machine learning perspective, like the more technical details of the how the market runs, or like the different topics of market might not be answered from me. Yeah, I will. Yeah.
Okay. Is there any question for the audience? At the moment, we have not question yet in the chat box or raise hand. Okay.
I think someone has the hand raised now.
Yes, this is okay. The question from Ahmad Yasir.
Mhm.
How can industrial demand response use AI to save electricity consumption without violating production, safety, quality, or comfort constraint?
Yes. So, as I mentioned before, like with traditional artificial intelligence, which kind of relates to the machine learning models and everything, full autonomy was not there, right? So you could only solve part of the problem. So like maybe for using demand response, or like to solve some questions of like, okay, what is my energy need going to be for the next hour, like you could use those to like forecast some of these things, but you always needed an human person to evaluate all the answers from these models, right? Because no matter how much an industry might have digitalized, uh, only the production manager knows properly like how each machine relates to each other, like what constraint might each machine have. So like fully making it autonomous with AI is not something industry wants to do, and is not something that is fully adopted in industry. So right now it's just simple forecasting methods or simple optimization methods there to aid human in the process only. And because of this point, like I also want to mention this is that my postdoc research, which is continuing at this point, now we are trying to focus on how large language models and AI workflows can be brought into this, so that it can be made more autonomous, right? So like then when we bring like AI agents and like large language model agents into the picture, now these models can not only evaluate results from like already existing forecasting models and everything, but if you are able to give grounded information, or like like information about your production process, maybe like PDF that your machine has, or like it could be a factory plan of like a certain production process. If we are able to provide this in a proper safe way to the LLM agent, then it would not just evaluate like what predictions happen in the next hour, but based on the predictions, can they be able to give good answers to the humans? So this is the more um, running question that is going on for my postdoctoral studies is to understand how to make this completely autonomous, or even if there is a chance of making it completely autonomous. So like we are trying to test what are the limits of using AI workflow and large language model in this context right now.
Okay, thank you, Atit. Is there any question before we conclude the Q&A? Okay, we'll look the participant who the raise hand. Wait. Yeah, you can open the mic for the participant who has
Test.
Dimas. Yeah, this is the last question from Dimas Arto. Yes, please open your mic and ask the question.
Test,
Hello,
test.
Dimas.
Hello?
Hello. Yeah.
Hello.
Hello. Okay, clear. Your yeah,
Am
you
I
can
heard?
ask your question.
Yeah.
Yes.
Thank you for the opportunity. My question is, since domain adaptation is about helping with less data than usually needed, could it introduce some kind of hallucination in generative models? If it could, what do you do to minimize it? Thank you very much.
Could you repeat the questions, please? Your voice was breaking up a little bit for me.
I'm sorry. Since domain adaptation is about helping with less data than usually needed, could it introduce some kind of hallucination in generative models? If it could, what do you do to minimize it?
Okay. Yeah. So, so when we talk about generative models, hallucinations happen when. So let's go back to this model over here. Okay. So generative models always work with the same architecture, right? Like the architecture is encoder and a decoder. Okay, so when you train an encoder and decoder, what you are trying to do is, like, for example, let's say, let's move out from the topic of electricity management and think about it in terms of images, right? So in an encoder and decoder architecture, what you would do is, like, first you would put in the image, the encoder would make a complex representation of your image, or, like, I don't know, like, you think of it as it compresses it into like some other dimension, and then the decoder then takes that representation and tries to create the image as best as it can to the original, right? So that's how the training happens. So when the training completes, so, like, let's think about complex architectures of chat gpt or like some llm model. We don't know how many encoders are there, how many decoders are there, but they will train their encoders in the same way, like they will train it to become a complex decoder, right? So when we talk about hallucinations, when hallucinations happen is because after the training is complete, what large language models do is they take out the encoder and keep the encoder over, like, in production. So when you are talking to a large language model, you are only talking to the encoder part, because decoder is then removed over there. So hallucination comes over here because there is not, like, there is not a loss function that monitors this decoding strategy at this point, right? So, like, from the probability space, your model starts to generate whatever it can generate. So I am not able to answer like how other models might reduce your hallucination, but in our case, like, we if you see in this image over here, we have this loss function while training the forecast, the decoder and forecaster, where there is a parameter called, if you can see my mouse over here, is my screen still shared? It is, right? So yeah, if you can see over here, there is this lambda parameter over here, right? So what this lambda parameter basically does is lambda, if lambda is really high, um, it will make the generation really random. So like, it will make something, that's when it starts hallucinating. But when like lambda is really small, what we are saying is like, try to make the feature space as close to like what you have learned. So like, in that way we are trying to like make sure that it does not deviate away from hallucinations in our model, to be specific. And in the reading, like I have more detail on like how the loss function is controlled with the lambda parameter if you go to the paper and read it. But yeah, I hope that answers your question a little bit about hallucination.
Hello, Dimas. Hello, is it clear?
Thank you very much for the answer, sir.
Okay. Okay, thank you, Dimas. I think the last question from Dimas is the end of the discussion, because as our time is up. Thank you very much. And thank you once again, Atit, for the valuable presentation and discussion. And thank you also to all participants for joining this session. And thank you all for all and I will now hand the session back to the Buroro. Thank you. Thank you all.
Thank you, Bu Linda. Thank you, Mr. Atit, for the speech. Thank you once again to our honorable speaker, Mr. Atit, and Mrs. Linda as moderator of today's webinar for the wonderful and insightful session today. We sincerely appreciate your time and dedication and valuable contribution to this event. The discussion and presentation delivered today have provided meaningful insight to the implementation of AI in industrial energy management, especially regarding technological barriers such as interoperability, computational complexity, optimization, as well as security and privacy issues. We believe that the knowledge shared in this webinar will broaden our understanding and inspire further innovation and research in this field. It has been a great honor and pleasure to have both of you with us today. And to our students, thank you once again, especially for the attending and participating in this webinar today. We are very happy to see such great enthusiasm, and I believe there were about more than 110 until 116 participants joining in this session. We truly hope that the knowledge and insight are shared today will be beneficial for all of us today. And we will now proceed to the photo session. We kindly invite all of you, the participants, to turn on the camera while joining the documentation session. It will be held by Mr. Denny. How many page, Pak Denny mau berapa kali take foto ini rencananya?
5, Bu.
3 kali aja, Bu.
3 kali, okay. We will have 3 pages, all the participants. Starting from 1, I will count from 3. 3, 2, 1. That was the first page, Pak Denny, and we have the second page now at 3. 3, 2, 1.
Bu, kakak.
Okay.
May ano to, MH to. MH Safira, Andika to.
Now is the last page,
Foto ni.
ladies and gentlemen. Okay. On 3, 3, 2, 1. On 1, I mean. Okay. Thank you, everyone. Thank you very much. Dear all participants, we will already come to the closing and prayer. Honorable guests and participants, reach at the end of today's webinar. We will officially conclude this event. Let us pray together. The prayer will be led by Mr. Yakin. Mr. Yakin, please proceed.
Ya,
Yakin, monggo.
marilah bersama-sama kita membaca doa kafaratul majlis sebagai penutup. Ya, kita baca bersama-sama.
Bismillahirrahmanirrahim.
Subhanakallahumma wa bihamdika
Asyhadu
astaghfiruka
an la
wa asyhadu an la ilaha illallah anta subhanaka.
ilaha illa
Zalimin. Amin.
Amin.
Thank you, Mr. Yakin. And on behalf of the organizing committee, I would like to express our sincere gratitude for all of you for the participation, for the attention and enthusiasm throughout the event. This is me, Roro Indah Melanie, as your master ceremony. Thank you for being part of today's webinar, and we will look forward to see you again at our future event. At the end, Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi
Thank you so
wabarakatuh.
much, Atit, and all participants.
Thank you, Mr. Atit. Thank
Thank
you, Bu
you.
Linda. Thank you for all of you. Yes, you may leave. Terima kasih semua.
Terima kasih Bu Roro.
Terima kasih semuanya. Sehat-sehat. Terima kasih
Kami
para
terima
mahasiswa.
kasih Bu Roro semuanya.
Bu Linda kapan pulang?
Siap. Nanti langsung
Siap.
makan-makan di rumah Pak Yakin.
Oh,
Oh iya, itu rumahnya Bu Linda kosong itu.
wah, Pak Yakin stalking.
Itu rumahnya malah jadian itu apa? Jadi sekretariat pesantren itu sekarang.
Mahasiswa semua terima kasih ya.